Hello everyone, I'm James Bonnar, an independent scientist from Racine, Wisconsin. So I have a story to tell you about my 30-year journey independently working on the application of artificial intelligence to gene therapy and cancer, as well as most other genetic diseases for that matter. So around 1992, I started an independent project trying to come up with a way to use AI, which I think of as machine learning, to do chemistry, chemical reactions to be precise. I was years ahead of my time. In particular, my end goal was to apply the algorithm to the prediction of chemical reactions involving DNA. This was not an easy problem, but I like challenges. After a while, I became completely obsessed with this one scientific problem. I studied science in a generalist fashion. I wanted to know just enough about all areas of science applicable to the task at hand, so I spent about 10 years in higher education. I had no specialty, nor did I want one. I graduated with a degree in physics, but was like one course shy of a degree in chemistry, biology, mathematics, and computer science. As soon as I finished my schoolwork, I dove into this problem very deeply. The main challenge was to find a representation for the chemical data that an algorithm could work with, and also finding the AI algorithm that could work with that representation. Then I learned about SMILE strings. SMILE stands for Simplified Molecular Input Line Entry System. These are ASCII text strings. But the main AI algorithm I had been familiar with was neural networks. You can't jam text into a neural network. You can only input-output numbers. So for a while I got stuck. So I remained stuck for several years. So one day I was exploring Mathematica's machine learning functions, in particular a function called predict. I tried inputting text strings and trained to equate them to numbers. I needed to somehow pattern match these SMILE strings, one for the reactants and one for the product. I concentrated on bimolecular reactions. So it occurred to me that each side of a reaction could be trained to the same number. That's it, I said to myself. I've accomplished something called string transformation learning. Now I was ready to train using a bigger set of training data. And I did. Next, I needed to test the generated model on novel reactants product pairs. So I did, and it was a perfect match. I was elated. So at this point, I needed a way to generate millions and millions of novel molecules to react in silico with the SMILE string representing the mutated DNA, and check each time if it equates to the same number as the healthy DNA string. The mutated DNA being reacted with a generated molecule. These are like medium-sized organic molecules. If so, it's a keeper. You see, these numbers can be spaced out far enough such that the odds are like 1 in a million that a match is a coincidence. Generating novel molecule strings was a tough problem, but I knew I had studied a computer program years ago that generated semi-random text from training data. It's a statistical approach called a Markovian text generator. So what I've done is not cure cancer yet, but I got us 99% of the way there. The remaining 1% of the work will be synthesizing the compounds the algorithm generates. The thing with AI is the answers it generates are not definitive. The experiments must still be done. But the algorithm I invented can speed up finding a cure at least 1,000,000-fold faster. So if you are a person or agency with resources such that you can afford to synthesize and test these compounds, say on the P53 mutations, please adopt the technology. I'm putting a link in the paper. I'm putting a link to the paper that details everything I did in the description below. Good luck to you all. Goodbye.